Today we're on page 10 of the Chapter 7 notes, section 7.7. Exponential functions are of the form y equals a times b to the x. Notice that the variable x is in the exponent. We're going to look at two graphs that are modeled on page 10 of the notes here. It says, observe how the graphs of exponential functions change based upon the values of a and b. So we have our general form, y equals a times b to the x. And the example, y equals 100 times 0.5 to the x. So our a value is 100 and our b value is 0.5. Now 0.5 is a value that is greater than 0 but less than 1. So our b value here is greater than 0 but less than 1. And if that's the case, your function is going to be decreasing. And if we look at the graph, right, this is a graph of y equals 100 times 0.5 to the x. Because our b value is greater than 0 but less than 1, our function is decreasing. So let's just go back up. If b is between 0 and 1, your graph will always be decreasing, or in other words, another name for decrease is going to be decay. So this situation here, as is noted at the bottom, is exponential decay. So if we look at our other example in the right-hand column, we have y equals 1 times 2 to the x. So our a value is 1, our b value is 2. And if we look at the graph is increasing, it's going upward. That will always be the case if our a value is greater than 0 and our b value is greater than 1. That's the greater than symbol. B value greater than 1. The graph is increasing. And again, it is typed out here. If b is greater than 1, the graph will be increasing. And again, in both cases, the a value is greater than 0. You could read that over again if you wanted to. I just wanted to highlight if b is between 0 and 1, you're going to have a decreasing function. If it's greater than 1, your function is going to be increasing. And at the very bottom, any quantity that grows or decays by a fixed percent at a regular interval is said to possess exponential growth or exponential decay. Next page. Two functions can be illustrated by concepts of growth or decay in applications. When a quantity grows by a fixed percent at a regular interval, the pattern can be represented by either growth, when you have y equals a times the quantity 1 plus r to the x, or decay, y equals a times the quantity 1 minus r raised to the x. You have to know these two formulas. So memorize. Two more things to memorize. For growth, y equals a times parentheses 1 plus r to the x. For decay, instead of a plus, it's a minus. Y equals A times 1 minus R to the X, where A is the initial amount before measuring the growth or decay. R is the growth or decay rate. Often it's a percent that needs to be changed to a decimal. And X is the number of time intervals that have passed. So looking at a few examples here. In the first example, we have a bank account balance, A, capital A, for an account starting with P dollars, earning an annual interest rate R, and left untouched for T years can be calculated as A equals P times 1 plus R to the T. Let me just go and write that, copy that formula. A equals P times 1 plus R to the T. This is an exponential growth formula because in parentheses we have 1 plus R. Find a bank account balance to the nearest dollar. Let's just underline that. If the account starts with $100, so this $100 is the starting amount, which is also known as our principal. Has an annual rate of 4%. 4%, that's our R value. And the money's left in the account for 12 years. So the 12 is our T value. Now, the rate is 4%, and you have to change percent to a decimal. To take 4% and change it to a decimal, you would take the decimal point in 4%, which would be after the 4, and you move it 2 places to the right. So R would equal 0.04. So R is 0.04. P is 100. Our P value was 100. And our T value is 12. So we pull from the written words our values for R, P, and T, and we're finding A. So we plug into the formula, substitute our values into the formula. So A equals 100 times, parentheses, 1 plus 0.04, and our time is 12. T value is 12. So that's 100 times 1 plus 0.04 is 1.04 raised to the 12. Now go to your calculator. And let's key in these values into the calculator. So 100 parentheses 1.04 close parentheses raised to the 12. 160.132219. 160.1032219. And we wanted to round to the nearest dollar. So that would be $160. So even though that was growth, the equation, the formula, was given to us. Right? And oftentimes when you're talking about money, instead of it being written y equals a times 1 plus r to the x, you're going to see the equation capital A equals capital P, P being principal, the initial amount, times 1 plus r to the t. Next, we have a population problem which reads, the population of Kingston in 1983 was approximately 35,000, with an annual rate of increase of 2.4%. So this is an increase, that's growth. So we're looking up at the equation above, y equals a times 1 plus r to the x. So let me just write that down. Y equals a times 1 plus r to the x. The 35,000, that's our a value, and our growth of 2.4%, the 2.4% is our rate. So when it asks for the growth rate, that's our 2.4%, but we want to write it as a decimal. So we would take the decimal point and move it 2 places to the left. So that would be 0.024. Write an equation to model the future growth, where y is the future or ending population, and x is the number of years since 1983. Number of years. Okay, so y is our ending population, so I'll continue here. So y equals 35,000 as our starting population. That's substituted in for a, times 1 plus 0.024 is our r value, and x is the number of years since 1983, raised to the x. All right, so that's our equation, and if we want, we can add that. I'm going to put the answer down here. So y equals 35,000, parentheses, 1.024 to the x. Notice our value here, right, is a value greater than 1, so we know it is increasing because it would represent growth. Part C, use your equation to estimate the population in 1991 to nearest 100 people. Well, 1991 is how many years since 1983? Well, 1991 is 8 years since 1983. So we're going to replace our x value with 8. So y equals 35,000 times 1.024 raised to the 8th power. And go to your calculator. $35,000, parentheses 1.024 raised to the 8th power. 42,312.40369. And to the nearest 100 people. Nearest 100 people. Well, the 3 is in the hundreds place. So 312 would round to 300. So 42,300. Now on the next page, page 12 of the notes, we have depreciation. When you see or hear the words depreciate, you're also thinking decay. We have Matt bought a new car for $25,000. The car depreciates or decreases by 15% of its value each year. So let me stop here. 15%, that's our rate. That's our R value. So R equals 15%. And since we're thinking of depreciation or decay, keep in mind the formula from the previous page. Y equals A times 1 minus R to the X. Part A says, what is the decay rate for the value of this car? All right, so the decay rate, that's our R value. So R equals 15%. As a decimal, that is 0.15. So that's our decay rate, 0.15. Write an equation to model the decay value of this car. All right, so for decay, Y equals A times 1 minus R to the X, or T. Okay, oftentimes instead of writing X, the lowercase letter T is written. Our A value is our starting value, that's our 25,000. So Y equals 25,000 times 1 minus our R value is 0.15 to the X. And 1 minus 0.15 is 0.85. So here's our equation. What will the car be worth in 10 years? We just substitute 10 in for X. Y equals 25,000 times 0.85 to the 10th. Key it into the calculator. $4,921.860109. Doesn't say anything about what to round to, but we're talking dollars and cents, so let's round to the nearest cent. All right, so 86, the 6 would be the cents. So $4,921.86 would be the value of the car after 10 years. And our last example, we have batting average. Jose went 2 for 5 in his first baseball game. His batting average decreased, all right, it's decreased, so we're thinking of exponential decay, by 0.3% each game. So the 0.3%, that's our R value. Poor Jose, he's not doing so well if he decreases each time. Part A, what is Jose's initial batting average after the first game? Well, batting average, after the first game, he went 2 for 5. So 2 out of 5 is equivalent to 0.4. Oftentimes it'd be 0.400. What is the decay rate for his batting average? That's our R value. So R equals 0.3%, which as a decimal, again, you're moving it 2 places to the left, so that's equal to 0.003. Write an equation to model his batting average after each game. So this is decreasing, so this is decay. This is y equals a times 1 minus r to the x, or t. His initial batting average at time 0 is 0.4, so that is substituted in for a, times 1 minus our r values, 0.003, to the t. And 1 subtract 0.003 is 0.997. So this is our equation. Again, you can have x or t there. I apologize, not just reading now. X is the number of games played, so these t's should be x's. So let me just go back and change that. Okay, so y equals 0.4 parentheses 0.997 to the x. And part D, what will Jose's batting average be at the end of the 161 game season? So we take our equation and we substitute 161 in for x. And go to the calculator. .2465928,497. We'll round to the nearest thousandths. So the 6 is in the thousandths place. Y equals 0.247. And we're done for today.